All right, so we're going to turn our attention to a new set of reactions, which are going to be broadly classified as nucleophilic substitution. If we kind of think about this word, substitution is going to mean swapping, and then nucleophilic means that we are going to be using a nucleophile. Remember, we brought that term up when we were thinking about acid-base chemistry. Nucleophile is going to be the group that has electrons that is going to do some attacking, most often like a base, where an acid is going to be more electrophilic. And there are going to be two main subclasses that we have in this nucleophilic substitution, SN1 and SN2. And we are going to have videos focused on each of those. So the general idea for each of these reactions, and the starting materials and the final products are the exact same. The only thing that's going to be different is the route in which we use to get there. We are going to start with a nucleophile, and a nucleophile is going to be our electron-rich species. It can be neutral or it can be negatively charged. If it's negatively charged, that's a kind of good kind of thing to kind of focus on and say like, oh, hey, that's going to probably be my nucleophile. We're going to react this with a substrate, and substrate is kind of a fancy word to kind of describe a chemical on which things are happening. And of that substrate, there's going to be a bunch of carbon stuff, which we kind of just call R here. And then connected to it is going to be some leaving group. And we're going to talk about a bunch of different examples of leaving groups. Some of the most common, though, are just going to be some of the halogens that we just learned to install in our last chapter. So a bromine, for example, is a nice example of a leaving group. And what's going to happen is we are going to substitute or switch our nucleophile and our leaving group. So in the product, we now have a new bond between our nucleophile and the R group. And then our leaving group has now been kicked off. There are going to be two main mechanisms in which this can occur, which are going to be our SN1 and our SN2. But the general process of identifying a nucleophile, identifying the leaving group on our substrate, and then swapping them is going to be the same throughout. Now, depending on the reaction conditions, how strong or weak the nucleophile is, how strong or weak the leaving group is, how good it is at leaving group, as well as other conditions. For example, what is our solvent? And there's going to be other things kind of above and below the arrow. So our solvent, we can think about things like the impact of temperature. We can also think about the actual R group itself and how does that promote or help one of those subgroups, SN1 or SN2, favor. So is that a big bulky substrate or is that a lot more open of a substrate? Those are going to be all the things that we're going to be kind of learning in our future videos. Now, we are not going to spend a lot of time talking about the idea of reaction coordinate diagrams. However, I wanted to show a little bit of a quick snapshot of a reaction coordinate diagram. Here are two different examples of a reaction coordinate diagram. And this is a kind of plot that we sometimes use in organic chemistry. So the x-axis here is the reaction coordinate, and that just simply means the progress of the reaction. So you'll have your reactants over on the right side, that's your starting materials, and then your products will be all the way on the right. So like over here, this would be, for example, like one of your products. The y-axis is associated with energy. So when you do a reaction, you're going to need energy in order to break bonds and make bonds. There's a bunch of energetics that's going to happen, and you're going to see this impact of the energy. There's an activation energy. So your activation energy is going to be a measure, and we're going to call that E sub A for activation energy. It's going to be a measure of how much energy you have to pump into your system in order to get over your transition state, which is going to be our highest energy spot. These can happen in multiple different ways. The first one, which we kind of show here on the right, is you start with a reactant, and then you do a reaction to form a reactive intermediate. And a reactive intermediate was what we introduced in our last chapter. We were talking about radicals, but we also have our carbocations and our carbanions. We're going to think a lot about carbocations being our reactive intermediate. So that's going to be a carbon with a positive charge. And then once you form that reactive intermediate, there's still a little bit, but you'll see this activation energy for your reactive intermediate is a lot smaller. So you'll then go from that reactive intermediate to a product. And those are two-step mechanisms where you form an intermediate species. There are also concerted reactions. Concerted means happens all at the same time, which is an example of the one that we have over here on the right. And depending on which one we actually have a different broad classification. So we have what we call SN1 and SN2 reactions. This first one, which is a two-step reaction, is known as an SN1, and the second one, which is a concerted, is known as an SN2. We'll go through and define that terminology in just a second. Now, a few other quick reminders. So your nucleophile is going to be your electron-rich species. A lot of times when you're thinking about your nucleophile, you're going to have to be thinking about things that have a negative charge. You don't have to. You can just have a lone pair that can act as a nucleophile, but a lot of times we'll see things that have negative charges, and electrophiles are your electron poor. So to kind of give some formal descriptions for each of these two different types, we have an SN1 and an SN2 reaction. SN1 stands for a unimolecular nucleophilic substitution. And the unimolecular, or the 1 in your SN1, is going to determine, or is going to be based on how many species are active in your rate determining step. And your rate determining step is going to be kind of the most important reaction in terms of like the energetics. That's kind of like the slowest step. And that step is going to be the one often that has the largest activation energy. So in your SN1 reaction, where you kind of see this reaction coordinate diagram, this very first step, when you go from your reactants to your reactant intermediates, that very first kind of step that has a really big activation energy, that's going to be the rate determining step in your SN1. And then once you form that, then both of the species, your nucleophile and your new electrophile, being that positive charge, are then going to combine together to form your products. So this happens in two steps, where just your reactant's involved and then your reactant and nucleophile is involved. SN2 has everything happen all at once. And with the fact that everything happens all at once, we do this bimolecular. And a bimolecular nucleophilic substitution is going to be when both of our species are going to be involved. And that's kind of a quick snapshot of just some high-level stuff thinking about this chapter. We're going to go in and spend 1 or 2 full videos on just talking about SN1. What does that mechanism look like, and what are some conditions that are favored in SN1, and do the same thing with SN2. The nice thing, though, is even though the route to get to the product is different, the reaction itself is going to be, the final product is going to be the exact same. We're going to identify a nucleophile, it's going to kick out a leaving group, and we're going to get a new bond between our nucleophile and our substrate. We're going to stop there, and in our next videos, we'll take a deep dive into SN1 and SN2 reactions.